Good morning. I'm Frank Devlin with APA, the Engineered Wood Association. Welcome to the third in our series of Engineered Wood Products training webinars. Today's topic is floor framing and rimboard construction details. Our presenter today is Nick Wartell, an APA Engineered Wood Specialist based in Atlanta. Nick is a graduate of the University of Central Florida with a BS in Design Engineering Technology. He has over 20 years experience in the building products industry, including truss design, engineered wood product sales, support, and management. Nick recently joined APA and covers the Atlanta territory, which includes Georgia, Alabama, Mississippi, and Central and Western Tennessee. Once again, welcome to the webinar. Nick, I'll turn it over to you.
Thank you, Frank, for the introduction. I'll be presenting APA recommendations on I-Joist and rimboard in residential floor systems. Individual manufacturer recommendations may differ. You should consult appropriate manufacturer's literature when specifying any engineered wood products. This module will cover recommendations for the installation of I-joist floors and rimboard. Layout and installation of floors impact both the real and perceived performance of engineered wood floors. Today, our training objectives, upon completing, students will be able to identify and describe the following: best practices in designing engineered wood floor systems, recommendations for rimboard in I-joist floor systems, proper techniques for notching and drilling I-joist and rimboard, and lastly, we'll talk about the correct use of web stiffeners, squash blocks, and blocking of I-joist floors. So to begin, the layout of floor members is more than a structural concern. Not only does the irregular spacing complicate the installation of the floor sheathing and other components, but also the perceived performance of the floor. As the occupants walk over areas where the spacing of the floor joists are irregular, the feel of the floor is also different. Size and space floor joists for the longest span then maintain the same size and spacing throughout the rest of the floor system, in spite of opportunities that might exist to spread the spacing over short spans. If value engineering overrides the performance concerns, make the spacing change at a distance from the point where the sheathing layout starts that is a multiple of 4 feet. That way, the staggered sheathing pattern is uninterrupted. Never mix 19.2 inch on center with other spacings. Otherwise, the sheathing pattern will have to be interrupted, as 19.2 inch does not divide evenly into 4 feet. A risk of mixing joist spacing is that occupants will feel the difference at the wider spacing where the sheathing must span further. As we just mentioned, homeowners notice a difference when they walk across the floor that has different spans of the same size floor joist installed in the floor, or the direction is changed on the same floor. Areas with joist spacing and spans may have more deflection in the joist and possibly the floor sheathing, depending on the type of finished flooring. This can lead to a homeowner feeling that the floor is weaker or softer in areas of greater spans or spacings, which can lead to possible dissatisfaction and complaints with the floor. Ideally, floors should be designed so that various spacings and spans have the same deflection. This can be done, but it will invariably lead to the use of different depths or strength classes of I-joists in various locations, which can be a logistical nightmare to try to get all those joists. However, not every floor that you'll be working with will provide an opportunity for the maximum use of joists and beam materials. Most of the time, layouts aren't as basic as the one on the slide. Consider using similar joist spans and spacings for consistent performance when you can, and understand the possible consequences when this isn't done. Today, we'll be walking through installation recommendations based on APA's publication, performance-rated I-Joist, Form Z725. This diagram calls out the various framing details that we'll be receiving. Note that all nails are common unless otherwise specified. First, we'll look at the various ways to provide a structural perimeter around our engineered wood floor system. The perimeter component is commonly referred to as rim board, rim joist, or band joist. This slide shows an APA rim board product used as a continuous rim joist. The rim board is attached to the sill plate or wall plate with 8D common nails, 6 inches on center. In addition, the rim board is attached to the bottom and the top flanges of each floor joist with an 8D common or box nail. This attachment laterally supports the floor joist and helps to keep it from rotating. Ends of I-joists require lateral bracing, which is achieved by the rim board. Also note that each side of floor joist is fastened into the sill plate or wall with an 8D common or box nail. Floor joist nails should be at least 1.5 inches away from the end of the joist and be driven at an angle to keep the end of the joist from splitting. When I-joists are sized to carry floor design loads, they often have little or no reserve reaction capacity available to carry loads from walls above that stack on top of the I-joist supports. This could cause reaction-type failures like web buckling or web knifing, unless the load from above is somehow transferred around the I-joist. Vertical load transfer is another function that can be served by rim boards. Each rim board product has a different capacity to transfer vertical loads as shown here in the table. It is important that the vertical loads are considered when specifying the type of APA-rated rim board that can be used. Keep in mind that structural composite lumber can also be used in this application, as long as the structural composite lumber rim board is at least equal to the height of the floor joists and no more than 1/16 of an inch higher. Detail 1A shows short I-joist section used as blocking to laterally support the floor joists and provide additional nailing for the wall sheathing and exterior siding. The I-joist blocking can be used to transfer vertical loads and lateral loads. The blocking has the capacity to transfer a uniform vertical load of 2,000 pounds per lineal foot. The blocking is attached to the sill plate or top wall plate below with 8D common nails every 6 inches on center. Note the 10D box nails may be substituted for the 8D common nail in this application. Rim board can also be used as blocking panels with the capacities as shown in the table on the last slide, i.e. the vertical load capacities are the same for continuous rim board or when rim board is used as blocking panels. Detail 1C illustrates an I-joist used as a continuous rim joist. Just as when using rim board, the floor joists are laterally supported with one 8D nail connecting the rim joist to each floor joist to the top and bottom flanges. When rim joists have flanges wider than 2 inches, the nails that are used to laterally brace the floor joist can be toe-nailed through the flanges. The rim joist is also attached to the sill plate with 8D nails 6 inches on center. Only APA performance-rated I-joists or performance-rated rim board should be used with I-joists. I-joists are typically manufactured to depths that are slightly different from sawn lumber. Engineered rim board matches the depth of I-joists and offers highly predictable performance and consistent quality. Because I-joists and engineered rim board are closely matched in moisture content, their moisture-related dimensional changes will be nearly equal, maintaining a tight fit and proper vertical load transfer from the wall above. Solid sawn lumber is not typically available in depths that match I-joists. Also, solid sawn lumber is produced at a much higher moisture content than I-joists and may shrink up to as much as an inch or a half inch, as it acclimates to in-service conditions. This shrinkage causes the nails to bridge between the floor sheathing and the rim board, reducing their ability to transfer lateral loads. It can also cause a gap between the rim board and the floor sheathing, setting up for the potential for I-joist webs to buckle. The major issue is the transfer of the vertical loads to the floor joists, which may already be at or near their bearing capacity, carrying the floor load to the supporting walls. The reduced capacity of the lateral load connection is of secondary and relatively minor importance compared to with a bearing failure of the I-joist, which can be an immediate life safety issue. There's no structural advantage to using solid sawn lumber rim board instead of engineered rim board. There is, however, a high potential for structural problems when rim boards are used as lumber. Let me reread that. I'm sorry. It wasn't real clear in my reading. There's no structural advantage to using solid lumber rim board instead of engineered rim board. There is, however, a high potential for structural problems when lumber rim boards are used instead of engineered rim boards. Hopefully that's more clear now. Let's look at holes allowable in rim board. Yes, the dryer vent can be placed through a hole in the rim board. And here are the hole cutting specifications. As you can see, a hole up to 2/3 the depth of the rim board can be cut. However, the segment of the rim board must be a minimum length for a maximum sized hole to be cut in order to transfer the vertical and lateral loads through the rim board. Additional holes can be made as long as the space between the holes is at least twice the diameter of the largest hole. When multiple holes are cut, the minimum length of the segment of rim board must be 8 times the sum of all of the hole diameters. And as with holes in I-joist webs, they should be centered in the depth of the rim board and cut as cleanly as possible. If a concentrated load is being transferred to a rim board, a hole can be cut through the rim board at a location no closer than the distance equal to the depth of the rim board from the closest edge of the area of the concentrated load. Builders are beginning to consider moving the headers from wall openings up into the rim board area of the structure. By doing this, they are multitasking the rim board while creating a better insulated wall area above the wall openings. Rim boards can be used as headers depending on the loads that they will require to carry, and are limited to a maximum span of 48 inches. As you can see, no holes are allowed in a rim board that is being used as a header. This table, found in APA's guide, Performance Rated Rim Boards, Form W345, provides you with design information for using rim board and rim board plus for headers. Please be sure to review the footnotes for additional design information. This graphic shows an application of rim board as a header, requiring a minimum length of rim board no less than 12 inches longer than each side of the opening. If a single rim board or rim board plus is not strong enough to carry the load, a double member rim board or structural composite lumber can be used as a header as well, but the maximum allowable span is still 4 feet. Rim boards can support deck ledger boards using a series of half-inch lags or through bolts. You can review recommendations for this assembly in several APA documents, including APA Performance Rated Rim Boards, Form W345, and the American Wood Council publication Design for Code Acceptance Number 6, DCA-6. Now that we've covered rim boards, let's look at other means of providing uniform and concentrated vertical load transfer where bearing walls are stacked above I-joist supports. As mentioned before, the intent is to transfer the loads from above around the I-joist so as not to exceed their reaction capacity. Squash blocks can be used, but they must be no shorter than the depth of the I-joist and no longer than the depth plus a 1/16 of an inch. Short lengths of dimensional lumber can be used on end, or short lengths of rim board can be used on their side. The use of short lengths of rim board for squash blocks eliminates the risk of cutting lumber squash blocks to the wrong length or cutting blocks out of square. This table identifies the vertical load capacity of pairs of squash blocks for transferring load of 2x4 and 2x6 bearing walls above the floor. It is important that squash blocks fully support the floor above and are fully bearing on the plate below. In some cases, a mix of full blocking panels and squash blocks are used when ductwork or wiring or piping needs to run through this area below bearing walls. An occasional blocking panel can be replaced with squash blocks so that there are open areas in the floor over the bearing wall or beams below the floor system. When blocking below a column supporting a vertical point load, make sure that the blocks below have an equal or greater area than the post or column above. If the vertical loads transferring through the rim joists are greater than 2,000 pounds per lineal foot capacity of a single I-joist, 2 I-joists or a rim board can be used. Also, if an exterior cladding material or siding needs attachment through the web of the I-joist, backing panels can be used to supplement any fastening requirements greater than what is than a nailable sheathing material can offer. Note that double I-joists are fully supported and do not require a filler block between them. The joist must be attached to the plate, and as discussed earlier, with 8D nails at 6 inches on center. Rim boards can also be doubled to transfer vertical loads. Before doubling rim boards or rim joists at the end of floor joists, make sure that at least 1 3/4 inches of wall remains available for floor bearing. When I-joist or rim board blocking panels are used, the attachment to the wall plate or beam below is the same as when used as a rim joist. The next topic involves openings in I-joist framing systems, or specifically how to connect I-joist to I-joist. This usually involves filler and backer blocks, as shown in this diagram. If a hanger load exceeds 250 pounds, backer blocks must be used. If the hanger is top-mounted, install the backer block against the top flange under the hanger. A face mount hanger must have backer blocks installed on both sides of the I-joist where the hanger is supported. Backer blocks must be long enough to keep from splitting when the hanger is installed. Use a nail long enough to penetrate the air thickness of the backer blocks and then clench when possible. Before attaching a face mount hanger to a double I-joist, make sure that the I-joists are assembled correctly, or make sure that the joists are assembled correctly. Attach the backer block where the hanger is going to be installed using 12 10D nails, which should be clenched on the back side when possible. The maximum capacity for this hanger is 1,280 pounds. The table here shows the thickness of backer blocks needed for various flange widths, as well as the maximum depth of the backer blocks. Any thickness combination of rated sheathing or sturdy floor panels will work. Utility-grade SPF lumber or better lumber can be used for 1.5-inch backer blocks. Double I-joists that carry uniform side loads must be assembled with a fastener schedule designed to transfer half of the side load from the loaded joist to the unloaded joist. An example is a double joist header at a stairwell. Use a length of nail that can be clinched if possible at each side of the double joists. If joists with a flange width of 2.5 inches or less, use 2 rows of 10D common nails at 12 inches on center on each side of the doubled beam, which means a total of 4 nails per lineal foot of joist. For joists with flange widths greater than 2.5 inches, use 2 rows of 10D common nails at 6 inches on center on each side of the double joist, or 8 nails per foot. The back of the I-joist web needs to be supported during nailing to prevent damage to the web flange connection. There should be an 1/8 to 1/4 inch gap between the top of the filler block and the bottom of the top flange of the I-joist, so that no unnecessary stress is applied to the web flange connection. The maximum side for this connection is 620 pounds per foot. This table identifies the size of the filler blocks to be used with each depth of I-joist, depending on the width of the flange of the I-joist. Again, any thickness combination of rated sheathing or rated sturdy floor will work, as well as utility-grade SPF or better graded lumber. The filler block is required to extend the full length of the span on the double I-joist, but does not need to be continuous. Connecting I-joists to solid headers is a little simpler. Hangers are being used to connect floor joist to a flush beam. In other words, the top of the beam is the same as the top of the floor joist. In this application with multiple beam members, the beams must be attached with a fastening schedule recommended by the manufacturer of the beams. The hangers can be either face mount or attached to the top of the beams. When face mount hangers are not as deep as the I-joist, web stiffeners are required for lateral support. Here's a top-mounted joist hanger on an LVL. Notice that the upper flange is laterally supported by the hanger, as is required. When the hanger does not laterally support the top flange of an I-joist, as we see in this photo, web stiffeners must be used to laterally support the joist. In this case, the web stiffeners are also required to accommodate hanger nails. Note the use of a skewed hanger in this photo. Here, top mount hangers are being used to connect the floor joist to a flush, non-nailable bearing wall or beam such as a poured concrete or a masonry wall or maybe a steel I-beam. Again, the top of the support is the same level as the top of the floor joist. The hanger attached to the 2x-plate. A stairway can be supported from a beam in an engineered wood floor. These beams are commonly composed of multiple I-joists or one or more structural composite members. If single or multiple I-joists are used, make sure that the multiple members are attached according to APA or the manufacturer's recommendations. Also ensure properly sized filler blocks and appropriate backer block panels are used to fill the web under the stair stringer hangers using 12 10D nails. The capacity of the hangers again cannot exceed 1,280 pounds. The ends of I-joists need to be restrained to prevent overturning. On the left, we see a hanger that does not laterally support the top of the I-joist. In the photo on the right, we see a hanger that doesn't provide lateral support to either the top or bottom flange. What do you think the issue is here? It's either the wrong size hanger or the wrong size joist has been installed. Web stiffeners are wood blocks that can be used for lateral support when joist hangers are not deep enough to reach the top flange. They might also be required to accommodate hanger nails. Both purposes are served in this slide. Web stiffeners might also need to be used to stiffen the webs of deep I-joists to prevent buckling at supports or to prevent webs from knifing through the flange at high reactions and high concentrated loads. PRI joist web stiffeners are attached with 4 nails. As the graphic indicates, either all 4 nails can be driven from one side and clinched on the other, or 2 are driven from each side of the joist. For joists having flanges less than 3.5 inches wide, 8D common or box nails are used. For flanges 3.5 inches wide, 10D common or box nails are used. The depth of the web stiffeners should be 1/8 to 1/4 inch less than the distance between the top and bottom flanges, so that no undue stress is placed on the connection joist between the flanges and the web during installation of the web stiffeners or the filler blocks. I'll reread that because it's very important not to jam wood in between the top and bottom flange. So what we indicate is the depth of the web stiffeners should be 1/8 to 1/4 inch less than the distance between the top and bottom flange, so that no undue stress is placed on the connection joints between the flanges and the web during installation of the web stiffeners or the filler blocks. Manufacturers of proprietary I-Joist products might have different web stiffener specifications. Consult the manufacturer's literature. There are 2 kinds of web stiffeners. Load stiffeners are placed over the web portion of the I-joist between the upper and lower flanges and directly under where significant concentrated or point loads are applied to the top flange of the joist. In this situation, the web stiffener is attached tight to the underside of the top flange, with a gap between the bottom flange and the bottom of the web stiffener. This application supports the load as it is transferred from the point load above and the joist into the top flange and the web of the I-joist. The second kind of web stiffener is a bearing stiffener, and it's located above the bearing points on either side of the span at the reactions. In this condition, the load is transferred from the bottom flange of the I-joist to the beam, bearing wall, or joist hanger below. Therefore, this web stiffener is installed tight to the bottom flange, with a space between the top of the web stiffener and the bottom of the top flange. PRI joist web stiffeners should be installed on each side of the I-joist and are only required to have a minimum width of 2 5/16 of an inch. The thickness of the web stiffeners depends on the width of the flange material, just as required with blocking panels, in order to create a surface flush with the width of the flange on each side of the joist. In general, PRI joist bearing stiffeners are required when design and reactions are greater than 1,550 pounds. Load stiffeners are required at locations where a concentrated load are greater than 1,500 pounds is applied to the top flange between supports, or in a cantilever joist between the cantilever tip and the support. Please check with your I-Joist manufacturer for specific recommendations for this and other installation requirements. Let's make sure that we're clear about overcutting holes, or notching, drilling, or cutting the flange of I-joist. It is not allowed. I'll repeat because it's pretty critical, and I know it happens in error. Let's make sure we're clear about overcutting holes. We don't want to disturb, notch, drill the flanges of I-joist. Cutting in the web is okay, but not in the flange. Okay, hole cutting is an important part of the installation of I-joist that is often violated. So before we move on, here's a quick review of the requirements. I'll just briefly hit some of the bullet points here. Limit 3 maximum size holes per span. An 1.5-inch hole can be placed anywhere in the web, provided it has the required distance from adjacent holes. Keep a minimum of an 1/8 inch between top and bottom of the hole and the flanges. I-joist top and bottom flanges must never be cut, notched, or otherwise modified. Whenever possible, field cut holes should be centered on the middle of the web. The weakest load is in the least stress is in the center of the joist, between bearing point to bearing point. And remember to make sure your holes are being cut in a workmanlike manner. Max size hole that can be cut into an I-joist web shall be equal the clear distance between the flanges of the I-joist minus a 1/4 inch. All right, now let's discuss the cutting of holes in I-joist by first reviewing how loads are transferred through the joists. The top diagram shows how the flanges carry the bending moments, which are greatest at the mid-span point of the joist that supports a uniform load. The top and bottom flanges must never be cut, notched, or otherwise modified. Never, period, never. Stay away from the flanges. The shear forces collect in the web of the I-joist and are the greatest at the supports as shown in the lower diagram, or the lower figure. The shear at the mid-span point of a uniformly loaded single-span I-joist is 0. This is the ideal location for any penetration through an I-joist. The closer the penetrations get to the supports, the greater the amount of shear forces, the smaller the allowable hole size. Here are some additional specifications for cutting holes in I-joist webs. Some I-joists have an 1 3/8 to an 1 3/4 diameter knockouts, which can be punched out carefully with a hammer. The knockouts are pre-scored in the web and are located from 12 inches to 24 inches on center along the length of the joists. These do not count as a hole and can be located anywhere in the length of the joist. The longest side of typical rectangular penetration should never exceed 3/4 the diameter of the largest hole allowed in the location in the length of the joist. A special case of rectangular holes is a duck chase, which would not follow this rule. Consult individual I-joist manufacturer for specific recommendations for duck chase holes. All holes must be sized and located in compliance with Table 6 of APA's Performance-Rated I-Joist Form Z725, or the sizing tables of the manufacturer of the I-Joist. A group of round holes at approximately the same location shall be permitted if a circumscribed round hole around them meets the requirements of a single round hole. There's a limit of 3 maximum sized holes per I-joist span. All holes should be cut with a sharp saw. For rectangular holes, avoid cutting the corners, which can cause unnecessary stress concentrations. Slightly rounding the corners is recommended. Start a rectangular hole by drilling a 1-inch diameter hole in each of the 4 corners. Then make the cuts between the holes to minimize the damage to the I-joist. Here's an excerpt from Table 6 in Form Z725. Note the distance from the inside face of any support or bearing to the center line of each sized hole. Your I-joist manufacturer will have a similar table that you can refer to. Let's apply Table 6, okay? But first, remember the requirement for the holes to be cut in a workmanlike manner. The rectangular hole looks too big, and the second hole looks like it's cut poorly. The location in the center of the web looks good, though. Let's assume that we have a 9.5-inch joist with a maximum sized hole of 6 1/4 inches. Assuming that the joist is a PRI 50 or equivalent joist, the center of this hole could be no closer than 6 foot 11 inches from inside of bearing. If the joist is actually spanning less than the maximum span, then the minimum distance to bearing will be reduced proportionately to the ratio of the actual span to the span adjustment factor, also known as the SAF in the table. So if the actual span was around 9 foot 7 inches, or 2/3 of the SAF length, the distance from bearing to the center of the hole would be reduced by 1/3, or down to 4 foot 7 inches. Here's what a formula would look like. To make the math easy, convert feet and inches into decimals. Hopefully you had time to review that equation as I was chatting. Let's look at a more complicated situation with the same series 9.5-inch joist. PRI 50. Looks like we have 2 holes very close together and close to bearing. That's a bad combination. If these combined holes are not more than 6 1/4 inches in diameter, they would have to be centered 6 foot 11 inches from bearing. And it looks like the center of the hole combined is actually about 12 to 18 inches from the bearing. This doesn't look like there's any way that the hole can be allowed, does it? This situation will require an additional evaluation by an engineer or the manufacturer of the I-joist to determine how to make it work. APA Form Z725, Performance Rated I-Joist for Design Construction Guide, includes many different cantilever details. This detail applies to a cantilever that carries a wall at the end. A table in Z725 will help you determine if this type of cantilever requires reinforcement. If so, sheathing may be applied to one or both sides of the cantilever to achieve the required strength. In this case, sheathing is attached to one side with 8D nails at 6 inches on center along the flange. Note the 2 foot maximum cantilever length and the 2 foot minimum backspan dimension. Cantilever supports are treated as intermediate supports, so at least 3.5 inches of bearing is required. And also note that blocking panels are required for lateral support at cantilevers. Here's an example of a short cantilever for 1- and 2-story residential structures in APA Form Z725. Note that the 2015 International Residential Code, or IRC, provides multiple fastening options, and this slide illustrates the most common applications. Cantilever joists must be properly sized to support all design loads. When bevel cutting I-joists, APA recommends that the cut does not exceed beyond the inside face of the bearing wall or beam. The full depth of the I-joist is to rest in part of the bearing wall or beam. Some manufacturers publish design recommendations and details for beveling I-joists beyond the inside face of the support. Consult specific manufacturer's literature before detailing I-joist or notching I-joist beyond the inside face of the support. When creating stairwell openings in an engineered wood floor, it is most common to place the stairs and stair opening running parallel to the floor joist. This usually requires a small header at the top and above the bottom of the stairs, and trimmers that run alongside the stairs. Obviously, if the stair opening is running perpendicular to the floor joist, the trimmers must be significantly stronger and typically more than a doubled I-joist. Design information for this application can be found in APA Technical Note Stairwell Openings in APA PRI I-Joist Floors, Form Z705, or from the manufacturer of your engineered wood products. LVL and other SCL members can also be used to head off floor joists and roof rafters for other types of openings, as shown here. We'll wrap up with a note about fire protection for I-joist floor systems. Both 2012 and 2015 versions of the International Residential Code, IRC, include fire protective membrane requirements to enhance the fire performance of residential floor systems. APA has a wealth of information about designing I-joist floor systems to meet the IRC requirements. Included a recorded webinar you can watch online, as well as downloadable publications and CAD details. If you have questions about I-joist or floor protection, visit apawood.org I-Joist webinar, where these resources are available for free. This concludes our presentation on floor framing with I-joist and rim board. Before we sign off, I'll review the training objectives, and then we'll review some APA resources you may find useful. So we talked about today in our training objectives best practices in designing engineered wood floor systems. We looked at recommendations on rim board for I-joist floor systems. Then we visited proper techniques for notching and drilling I-joist and rim board. And lastly, I discussed correct use of web stiffeners, squash blocks, and blocking for I-joist floors. APA has many other resources available for you as well. We all need help from time to time, and APA's Product Support Help Desk is a great source for answers to those questions that you run into during your work with engineered wood products. The Help Desk is a free service and is available to answer your questions pertaining to the specification and application of engineered wood products and systems. It is staffed by specialists who have the knowledge to address a diverse range of inquiries related to engineered wood, and this is not only a fantastic resource for you, but also your customers, builders, designers, and code officials. The APA Field Services team consists of full-time engineered wood specialists located throughout North America. These engineered wood professionals include engineers, architects, and construction experts who are available to provide information and recommendations to construction and design professionals. We recommend that you get to know your APA wood specialist in your area. APA has updated and redesigned the apawood.org site. The site holds a wealth of information about products and their recommended installation requirements, and all electronic downloads are free. Take a few minutes to explore the site so that you'll be familiar with the resources that are available. Also, on the APA website, there's a list of APA members, including complete lists of the manufacturing facilities and their sales contacts. APA has a large selection of literature, some which will be referenced during these training modules, and all these documents are available for free download from the APA website. And finally, from the apacad.org website, designers can download many different details that can be dropped directly into their design. this concludes our training module. It looks like we have some time for questions.
How do I determine the size of a beam or joist to use if more than one works based on my span and load?
Okay. Let me give it a couple seconds to gather my thoughts on that one. I would say the best place to start is figure out what products are available in your area. Availability of joist series and depths is critical. You certainly don't want to specify a product that's not readily available in your marketplace. Next, I would determine if you have height or on-center spacing restrictions. It's always best to compare overall floor system cost as compared to the lineal cost of just the price of the joist. When comparing systems, you'll find that you can increase the depth of the floor, and it'll allow you to increase your on-spacing. By doing this, you can design a floor with less joists, overall reducing your cost of the floor system. The last thing I would definitely take in consideration when choosing the correct depths of beam or joist to beam would be deflection criteria. If you've got marble floors or thick mud concrete that has to be poured under that marble floor, you've got to have stiffer deflection criteria, and that could govern the on-center spacing as well as the joist series that's required for that particular design. So it's really kind of a complex question that you really need to kind of look at the overview of the structure and then see what the controlling factor is in that structure. Sorry to be long-winded there, Frank. You got any more?
No, that's good. We do have a couple more questions. Are web stiffeners required in I-joists when installing hangers?
Some hangers don't require web stiffeners, but when the joist top flange is laterally supported by the sides of the hanger, we don't need to add a web stiffener. Although a designer may want to check, make sure the reaction forces are not excessive, because remember, there's web stiffeners required for increased allowable. When there's point loads coming at stiffener locations or hanger locations, a lot of times web stiffeners need to be added. So check with your manufacturer's recommendations when in doubt.
Thank you. Good stuff. Now, where is you went over this a couple times, but where is the best place, again, to cut a hole or notch an I-joist?
Well, that's a great question. I mean, it can't be reinforced enough. I-joist stresses are lowest near the mid-span between two bearing points. The stresses are highest as you get closer to your bearing locations, your supports. So when you can kind of pick this up when you look at the hole charts for I-joists, where larger holes are always going to be permitted in areas further from bearings. And remember, don't notch or damage the flange of the joist. That's the critical. A lot of your load transferring capacities in the top and bottom flange. The web is the only area you can cut the holes.
Very good, thank you. Can rim board be used as headers over traditional 32-inch wide basement windows?
It depends on the applied load. Even in most residential construction, you can do that. However, it applies only when the design load does not exceed the rim board capacity. APA has kind of a guide for that, and that can be found on, I believe it's W345. So if you want to make a note of W345, it might be a good document to check into.
Okay, good, thanks. Form W345 for those basement window applications. And
Gotcha.
When do I need blocking over interior bearing supports?
I-joist or rim board blocking is required on all interior load-bearing walls or where I-joists are not continuous over the support.
All right, very good. Well, that's all our questions for today, and that's the conclusion of our webinar.